Welcome to topic 4, Dr. Come Quick, the anatomy of an aerospace craft. Over the next two videos, we will talk about different parts of aerospace vehicles. Take this in. Fumbling for his recline button, Ted unwittingly instigates a disaster. Think about what this means in terms of different parts of an aerospace vehicle. Also think about what type of vehicle this is. Your questions for the next two videos. What are the key components of an aerospace craft or vehicle? Are there any common themes? Are there things that are shared between atmospheric and exo-atmospheric or aero and space vehicles? There are going to be a lot of these. Some of the things you thought weren't common are going to be common. But also think about what is unique for these different types. Because some of the things you thought were common may be unique. Also, at the end of this, think about, can you remember what those are? Because you will be expected to answer questions on the midterm exam and the final exam on these topics. Before we continue, one bit of advice. Please take notes. The more you write down here, the better prepared you will be for whatever comes next. Okay, our first section will be atmospheric vehicles, both fixed and rotary wing. In this second video, we will talk about space, launch vehicles, and satellites. So starting with fixed wing, what do we have? This is a cartoon version of a fixed-wing commercial transport, courtesy of NASA. As you can see, on this, we have different aspects. First, we have the horizontal stabilizer, which we use to control pitch. We have the vertical stabilizer, or rudder, which we use to control yaw. Elevator changes pitch, rudder changes yaw. We have our wings and our fuselage. We have ailerons to roll. We have flaps to increase lift, spoilers to change lift and drag, and often roll, slats as part of the high lift system, our cockpit or flight deck for seeing, and of course our engines. Understanding what each of these terms are, what are their other names? So for instance, the horizontal stabilizer is also known as the horizontal tail or just tail, and the vertical stabilizer may also be known as the fin, is really useful. You'll have to understand that and what they mean. But as we look at these aircraft, we're going to understand how they're different from one fixed-wing aircraft to the next. Because some of these are not on every aircraft. For instance, lots of general aviation aircraft and business jets don't have slats. Some don't even have flaps. Some fighter aircraft don't have ailerons. Or they have an all-moving stabilizer. They don't have elevators. The whole stabilizer controls pitch, not just trim. Maybe they have an all-moving fin. Maybe they don't have a cockpit. Maybe they don't have a fuselage. So think about that. There's no one common identical thing in fixed-wing aircraft, but these parts come back again and again. So if we look at a real aircraft, this is a good example in drawing. Can you guess what aircraft this is? For those of you who guessed the Boeing 787, you're right. I chose this mainly because it's well drawn. Some of the other ones don't have this. You can see the slats on the leading edge of the wing. Obviously the engines. We have our inboard and outboard flaps and our ailerons. There's actually another aileron here you can't see. We have our horizontal tail or stabilizer, and the elevators, our vertical tail stabilizer. We have our landing gear, our fuselage with the doors and windows, and our flight deck or cockpit windows. This bit back here is the exhaust for the auxiliary power unit. Again, it's something on some aircraft, but not all aircraft. So thinking about that, we have our fixed-wing aircraft. Now, let's look at a rotary wing aircraft and see how those compare. So this is a helicopter, a single main rotor helicopter. Obviously, you can read, it's the Bell UH-1B Iroquois, also known as the Huey, made famous by the US military in the Vietnam War. We have different components. We still have a fuselage. We still have a fuselage. We still have a flight deck or cockpit. We still have a horizontal tail and a vertical tail. Now, instead of wheels for landing gear, this one has skids. But what about propulsion and lift? On our fixed-wing aircraft, we had separate engines and wings. On a rotary-wing aircraft, they're combined. We have our main rotor. And our main rotor provides both our lift and our ability to move forwards. Obviously, the power in this case is generated by a single small turboshaft gas turbine engine, but it is transmitted through one component. Now, can anybody guess what this component is, what it is and why it exists, and why we don't see it on other types of rotorcraft and other types of helicopters? You're right, it's the tail or anti-torque rotor. And what happens on a helicopter is we spin the main rotor one direction, the fuselage, the rest of the helicopter wants to spin the other way. If let spin freely, the helicopter won't fly. So we include the tail rotor in for that control. On a tandem helicopter with two main rotors, or a multi-rotor that's 4 or 6, we can do that by having counter-rotating rotors overall. We don't have to have that tail rotor. Now, we're going to talk about something that's unique to helicopters, and specifically helicopters that use blade pitch for control. So single main rotor, tandem intermeshing type helicopters, not the multi-rotors you find and buy from DJI. And that's called the swash plate. And this is at the hub of the main rotor. And as you can see, you have your main rotor blades here, here, and here. And to control our helicopter, to make it go up and down, side to side, fly forwards, bank, all of that, we change the pitch of rotor blades, either collectively in concert, that allows us to go up and down, or individually as a cycle around the hub, called cyclic. And that's done through what's called a swash plate. And what this is everything above this rotates and the bits below are fixed and connected to our controls. If we move the whole swash plate up, it increases the pitch on all of the blades simultaneously, independent of where they are in their cycle. If we move the whole swash plate down, it does the opposite. So that allows us to go up and down. If we tilt the swash plate side to side, it changes the blade, the angle of the blades, as they go around. They go up, they go down, they go up, they go down as the blade goes around 360 degrees. And what this does is it causes the helicopter to pitch either forward or backward or side to side. And that changes the thrust vector and allows us to accelerate forward, slow down, accelerate backward, accelerate side to side. If we want to turn, we'll do that at speed, not when we're hovering. We'll do that banking, the side-to-side tilting, and we'll couple it with the tail rotor to turn the front of the helicopter. So this is something that's unique to rotorcraft, and specifically a subset of it. You don't see this on fixed-wing aircraft. However, there is a small subcategory of fixed-wing aircraft that behave like rotorcraft. Can you think of what those are? I'm not going to tell you in this video, however, we can discuss it in the live sessions. Okay, so that brings us to the end of video number 1. In the next video on this topic, we will talk about space vehicles. We're going to talk about both the launch vehicles and satellites and the key components of those. So stay tuned.